Welcome to Hot Chips 2023. Tutorial 2. Chiplets, UCI.
We have an exciting talk today on UCIe. So there's just a slight change in schedule, and I'll go over that. Just before we begin, just a couple of announcements, right? So all the speakers are here on behalf of UCIe Consortium. So they're not going to be able to answer anything about products or product timeline. So if you can refrain from asking those questions, it'll be helpful. There's a minor change in the schedule. So the electrical stack is going to be just before the break, but we'll take the Q&A after the break. And then, on behalf of the Hot Chips Committee, we request you don't live stream the content while in the auditorium. And finally, during the Q&A session, if you can please come to the mics and state your name and affiliation, that'll be very helpful. Okay, so the first session on UCIe overview and usage models is going to be presented by Dr. Debendra Sharma. He is an Intel Senior Fellow and co-GM of Memory and I/O Technologies in the Data Platforms and Artificial Intelligence Group at Intel Corporation. He is a leading expert on I/O interface and subsystem architecture. Debendra is a member of the Board of Directors for PCIe SIG and Chairman of the Board of Directors of the UCIe Consortium. He also co-leads the CXL Technical Task Force, and he's made significant contributions to all three of the industry consortiums. Debendra has a bachelor's degree of technology in computer science and engineering from IIT Kharagpur and a PhD in computer engineering from UMass Amherst. He's been awarded the Distinguished Alumnus Award from IIT Kharagpur in 2019, the IEEE Region 6 Outstanding Engineer Award in 2021, the first PCI SIG Lifetime Contribution Award in 2022, and the IEEE Circuits and Systems Industrial Pioneer Award in 2022. Please welcome Debendra.
So Universal Chiplet Interconnect Express, that's UCIe. We are an open consortium, 120 plus member companies. Here are the board members and growing. And there are two broad levels of membership, contributor level and adopter level. A company decides what's appropriate for them. So that's a brief introduction to UCIe as an open industry standard body. Next, we'll talk about on-package interconnects. What are the opportunities and what are the challenges? Gordon Moore is well known for his 1965 seminal paper in which he predicted Moore's law. In the same paper, he had also predicted the day of reckoning. And he said that it may prove to be more economical to build larger systems out of smaller functions that are separately packaged and interconnected. That day of reckoning is already here. If you look into the volume CPUs, whether it is client, server, GPUs, anything, those are all constructed today out of chiplets. So that's the background. And what are the drivers for this on-package chiplet? We are all up against the reticle limit. Yield is a challenge in the more advanced nodes, so larger dies yield less. And in general, the demand for scalable performance continues to be unabated. So what people are doing is basically they're putting multiple dies on the same package, and that's how they're delivering the performance. So this is what I call scale-up kind of applications, and that's what we see today. The other thing is around the increasing design costs at the leading edge process nodes. So the graph here that you see, it basically portrays for different process node, what is the cost of porting an IP? And that's a well-known study, and you can see that those are getting fairly expensive. And disaggregating things into smaller chiplets and putting them on the on the package helps us not pay for porting those IPs that don't really need to change. Also, by having chiplets, we can have late binding by having time to market advantage. Things that are in flux, those can be just in time kind of IPs. You can put them on a separate chiplet and connect them later on. Also, the other advantage is, we'll talk more about this, bespoke solutions, custom silicon, where you can have different customers have different needs. For example, different customers need different acceleration functions. If it is in a chiplet, then you can decide what kind of mix and match you can have. And of course, different process nodes are optimized for different functionality. Things like, memory likes a different process node, logic, different one, analog, so on and so forth, co-packaged optics. So these are the drivers for the on-package chiplets. Then the question is, what does it take for us to make an interoperable chiplet-based ecosystem? And the short answer is, it's all four of this, right? So if you start from the bottom, we have the die-to-die I/O. This gets a lot of visibility. Of course, it's very important, the physical layer. Next is, what protocols run on top of that? How do you do the SoC construction? What's the chiplet form factor, right? All of these are important aspects that are required to ensure that you have an interoperable chiplet-based ecosystem. So fundamentally, the design choice, today, if you look on the picture on the left-hand side, over here, we are very successful for multiple decades now of building composable systems at the board level. You can get your CPUs from somewhere, you can get your DIMMs from somewhere, you can get your PCI Express CXL cards from any number of vendors, put them on a board, assemble them, and they just work. And things that have made those things possible are standards like PCI Express, recently CXL, all of those things. We want to take the same construct and apply them at the package level, and that's what the picture in the middle shows, where, oops, wrong one, where you can assemble different chiplets doing different functionality and then form effectively your SoC at the package level. And then, more on-level integration, on-die integration is also possible, right? People can take that functionality, move them on die. And as I said, a lot of these constructs are where people are taking, because the die size is increasing, they're moving the other way around for yield and other reasons, right? Reticle limit, all of those reasons. So we need to think about having the same software, the same IP, the same subsystem to build these scalable systems that offers us the economies of scale advantage. So now let's talk about UCIe, which is an open standard for chiplets. Several of us have decades of experience in making PCI Express successful. We have worked with PCI Express from the beginning, not just me, but a lot of my colleagues, right? We are all involved with UCIe, CXL, some people have worked on USB. So we know what it takes to build an open ecosystem, open, successful ecosystem. So these are based on those experience. The guiding principles for UCIe have been open ecosystem, of course, plug and play, with full backward compatibility evolution, because you want to make sure that people's investments are protected. Best power, performance, cost metrics across the entire industry, so that you can support not just one segment of the market, but the entire compute continuum. That's important. Otherwise, you become a niche technology. Not that there is anything wrong in becoming a niche, but our aspirations are, these interconnects will span everything from your handheld to your supercomputers. And of course, you have to continuously innovate to meet the needs of the evolving computing landscape, because for anything that goes for multiple decades, you cannot be static. You need to continuously evolve, right? The world evolves. And so with that, the vision of UCIe is to align the industry around an open platform to enable chiplet-based solutions. If you look at the picture here, you can have C of cores, which are multiple chiplets. You can have acceleration functions. You can have memory. You can have, things like co-packaged optics, things of that nature. And you want to be able to do that across, doesn't matter where people manufacture their chiplets from, which foundry where they assemble it, and it's like heterogeneous integration, just like it happens at the board level with PCI Express and CXL. So this basically goes through what we talked about. So you want to make sure, of course, you want to make sure that the scale-up construction is preserved, even with the UCI. People are going to run their proprietary protocol, just like today, right? If you look into the symmetric multiprocessing protocols that are used to construct 2-socket, 4-socket, those run on PCIe 5, but they run their own proprietary protocol. We need to support that. But at the same time, we need to make sure that the heterogeneous integration happens. Of course, we'll want to make sure that all the other goodness is preserved, like time to market advantages, cost advantages, and of course, you want to be able to offer bespoke solutions to your customers, and of course, scale the innovations. Now, again, coming from our experience, there are two broad set of things that make a standard successful. It's not a either or, it's and. You need to hit all of them. So first is what we call key technology metrics, and things like, in the context of die-to-die, it is bandwidth density, both linear density as well as areal density. That's dictated by data rate and bump pitch. The other one is energy efficiency in terms of picojoule per bit, not just the picojoule per bit that you consume when you are doing full transfer, but also what is the power consumption when the bandwidth demand is not at the peak. For example, if my bandwidth demand is 10% of the peak, ideally I should consume 10% of the peak power, right? That's the scalable energy consumption, and that's dictated by low entry and exit latency, and also how much power you save. And we'll go through some of these numbers in the talk today. Latency is important, channel reach is important, technology independence is important, right? All of these things are important. Reliability and availability, super important, and then of course cost. So you'll see that that's why we support standard packaging and advanced packaging. On the other side, you want to make sure that for adoption there is interoperability. So you need to define a full stack. If you can't just give a PHY to somebody, it will be the moral equivalent of giving a PCIe PHY and saying there is no other stack, no software, nothing. What do I do with that, right? So you need to give a full stack, needs to be full plug and play. Working with existing software stack, it's a huge plus, right? Lowers the barrier. Different usages and segments, you need to make sure that you're supporting all of that. And of course, technology independence. So you need to make sure that whatever you do applies across different process nodes, different packaging options, power delivery, cooling, all of those things, right? And in general, you want to make sure that there is broad industry support and an open ecosystem. You can hit everything else. If the broad industry is not there, it's a fairly lonely place. So UCI has been architected and it has been designed from ground up to meet all of these needs. Now let's look into the specification, and then people are going to go and do deep dive into each and every one of these layers today. UCI 1.0, and we recently did UCI 1.1 specification, both of them. That's UCI 1.1 is backward compatible with UCI 1.0, comprehended a few needs like automotive and all of those things, but it's a layered approach. And again, that's nothing new. PCI Express is a layered approach, so is CXL, so is USB, right? And it has got industry-leading key performance indicators. We'll see the numbers. Physical layer talks about die-to-die I/O. So this does everything like link training, lane repair, lane reversal, scrambling, analog front end, of course, clocking, clock distributions, sideband, config registers. All of those things are comprehended. And the physical layer talks to the upper stack, and of course bump and bump map, all of the fun factors, those are defined. We have a raw die-to-die interface, RDI, which is specified in the specification. That talks to the die-to-die adapter. The die-to-die adapter is equivalent of what we call, for example, link layer in PCI Express and other protocols. So this is a multi-protocol capable die-to-die adapter. People can bypass it if you are using in raw mode, for example, if you want to just connect to a SerDes die and you have your own networking stack, right? Then you don't need the die-to-die adapter. That's fine, you can bypass that. And it also has things like CRC, replay, all of those things. And then on top of this, there is a Flit-aware die-to-die interface, which interfaces with the protocol layer, which can be PCI Express, CXL. And recently also we added the streaming protocol to take advantage of the die-to-die adapter. As I said, protocol layer wise, we support CXL and PCIe natively. And that's there for volume attach, plug and play, very successful standard. So a lot of the SoC construction issues are addressed by PCI Express and CXL protocols. Those are the ones where people know how to make it work at the board level. They need a clock and they need a power and off they go, right? So those are there, and of course usage cases are covered, like IO attach use case, memory use cases, accelerator use cases. Those are all covered with CXL PCIe. Streaming protocols are used for things like scale up, things like a lot of people like to use HC, Chai, those kind of things. So we have provided the streaming protocol support. And the specification scope is from here all the way up to here. So any kind of metrics we give is inclusive of everything. Well-defined specification, we're keeping in mind interoperability and future evolution. And we talked about config registers in each and every one of those layers so that you can do link discovery, all of those things. Form factor, manageability is comprehended. Compliance is very important. We'll talk more about that today. And of course, plug and play, right? I mean, you can see that even at an IP level, we have defined these interfaces so you can get these IPs from different places, stitch them together on your SoC, and they will work. UCIe 1.0, it supports both standard package as well as advanced package. So standard package, it's for cost effective, things that are at a longer distance, so like 25 millimeters. So you can have, these are similar to what you do at a board level, right? You got your bumps that can be 100 to 130 micron, depending on the technology, between bumps, spacing between bumps. So you connect them on the package level, and this distance can be up to 25 millimeter. We also support advanced packaging, which is 2.5D. These are for power efficient, very high bandwidth density, and we are going to see the numbers in a few slides here. And we give 3 examples, and these are just examples, not meant to be an exhaustive list, but just goes to show that the technology really is independent of any kind of process node and any kind of packaging technology. So on the very top there, it's Intel's EMIB technology used for advanced packaging. The one in the middle here is TSMC's CoWoS. The one at the bottom, third example, is ASA's Focus. So, the basic vision here is that your dies can be manufactured anywhere and they can be assembled anywhere. And you can even mix 2D, 2.5D on the same package. So one specification that supports a broad range of these usages as well as packaging technology. We'll go through some of these in much more detail, as I said, in the subsequent presentations, but UCIe is architected with, of course, process portability in mind. So the bump out in the specification, it talks about interoperability, even with future bump pitch reduction. So, for example, this shows the UCIe S standard, the bump out both for stacked and unstacked. This is the advanced package bump out. So you can see that this is 55 micron. So advanced package goes from 55 micron down to 25 micron with 1.0, 1.1. So 55 to 55, this is what the connection will look like. Basically what happens is that we define a fixed beachfront, which is 388.8 micron. So if you connect, somebody has a 40 micron bump pitch, then their depth will be less because it's much more tightly spaced, but then the beachfront is still the same, and that's how you can connect. So you can connect across different technology choice points. Now let's talk about the physical layer. The basic unit is a module. You can have one module, you can have two modules, or you can have four modules in order to form a link. And of course, you can have as many links as you want, but this is like one single entity link, right? A single module, 2 modules, or 4 modules. Each module is, if it is standard, it is 16 lanes, single-ended. If it is advanced, 64 lanes, single-ended. 1 lane for valid, single-ended. 1 differential pair for forwarded clock. A single lane for tracking, which is used for calibration. We support lane reversal mandatorily on the transmit side. For reliability, advanced packages have spare lanes, and standard packages go through link degradation, similar to what happens in PCI Express and CXL, external links. We support a wide range of frequencies, 4 GHz, 8 GHz, 12, 16, 24, 32. If you support a frequency, you must support all the lower frequencies, and that's what guarantees interoperability. You don't have to worry about should I design to 16 or should I design to 12? Where will people be there? Well, if your chiplet needs 16 GHz, design to 16. If somebody else designs to 12, you are going to run at 12. Same way that happens today with PCI Express, right? You have a range of frequencies, they all interoperate. Now, the bandwidth per module, just to give an idea, is 64 gigabytes per second for standard, so 256 gigabytes per second for advanced. So for example, the advanced package, a single module, is the equivalent of a by 16 PCI Express Gen 7 bandwidth running at 128 gigatransfers per second. So 2 modules will get 2x of that, 4 will of course get 4x of that. And sideband, it's always on. There are 2 lanes, one for clock, one for data, 800 megahertz, and it's used for link training, debug, bunch of other things which are extremely useful. And we don't really lose source lines. We basically have depopulated some of the ground pins to make room for the sideband. And the valid is used for effective dynamic power management. Die-to-die adapter does Flit mapping through the FDI interface. It's responsible for the packetization, and there are 3 sets of examples given here. You will see that fundamentally it's a 2-byte CRC that protects up to 128 bytes of data, and you will see that there is 256-byte format which PCI Express and CXL use, where those 2 byte of CRC is at the end, or you can do the latency optimized version where 128 bytes covered with 2 bytes of CRC, the next 128 bytes is covered by another 2 bytes of CRC. This guarantees triple bit flip detection, and if there is a CRC error, you're going to do a replay and get the packet back. And of course, the sample RTL code is there in the spec. Now let's talk about the usage models for UCIe. Of course, the primary purpose is to enable SoC construction at the package level, right? Mix and match of chiplets of different functions so that you get the desired functionality. So in this example here, what you see is 4 processor nodes, and these are in the most advanced process node, memory and IO controllers. So this might be in a prior generation process, right? You have a mix of different types of accelerators. You have got some amount of memory, you got RF, you got modem, you got optical, you got analog, so all of these things, right? So processors might be using symmetric coherency by mapping UCIe over FDI. Memory will be CXL.mem, accelerators can be PCIe CXL, and you can have the mix and match here, right? And somebody might put different types of accelerators instead of these types. Somebody might decide to put maybe 2 processors and more accelerators. You can do the mix and match, right? That's the beauty, right? They all speak the same protocol, so you can do mix and match of things. And the vision here is, again, right, we want the technology to be up, and it is targeted across the entire segment, and that's why there is such a wide range of KPIs, right? You saw that, a wide range of frequencies, wide range of width. So from handheld to client to server to workstations, you name it, right? We want to cover them all. And UCI PHY and the die-to-die adapter, these are common. So you got the different protocols that we had talked about, and that's how we can do this mix and match. Now this is another example of the SoC construction from the previous slide. In this example, this is a switch construction. So for example, we might decide that a 128 lane CXL switch is the sweet spot in the market. It can be a networking switch for all, it doesn't matter. This is just an example, right? So if it is a 128 lane, that is the sweet spot. Well, what do you do for larger switches? You can always, of course, do another tape in with 256 lane switch, another tape in for 512 lane switch. Who knows whether you can be within your reticle limit or not. The other option is what we are showing here, right? You use UCIe, the switch's internal bus protocol will get transported through that UCIe PHY using the potentially the die-to-die adapter. 2 of them together, you get your 256 lane switch. 4 of them together, you get your 512 lane switch, right? So again, this is how you do the scale-up construction. And if you look into even our, in my company's Xeon, for example, Sapphire Rapids, that's what it looks like, right? 4 dies together connected through our own MDFI, which is basically a precursor to predecessor of UCIe, connected together using EMIB, and that's how we construct. And other companies are doing the same thing, right? So nothing new here, right? I mean, these are well-known, well-tested methods. Another example of scale-up is given here. So in this case, you got 2 sets of cores that are connected using CHI interconnect over UCIe, and on this side with accelerators, they're connected using either CHI or CXL. So this can be your true plug and play, right? So again, the same SoC construction using mix and match. This is a different type of usage model, and it's basically off-package connectivity with retimers, UCIe retimers. So UCIe is an on-package interconnect, right? And the vision here is that, especially with things like co-packaged optics, you can put the optical die as a UCI chiplet and escape the package. If you can do that, what are the things that you can do? See, for example, here, you can imagine that, this is a multi-domain as in multiple servers, right? You got different set of compute servers here. You got a pool of memory, pool of accelerator, pool of storage, infrastructure processing unit connecting to a network, and you got the load store fabric fundamentally, which is a CXL protocol. But these are all connected through optics using UCIe as the basic interconnect. Physically, this is what it looks like. You got your rack subserver and they're connected. You got your different compute nodes here. You got your pool of storage, which can be in the same rack, can be in a different rack. It can be across the pod. And at the each package level, right, you can see that this is where you have, for example, the CPU package. You got your cores, you got your memory and I/O. You got some on-package memory, off-package memory, CXL PCI, and then you got your UCI retimer through which you are exiting the package using an optical connection. And then this is the switch construction that I showed, can be through the UCIe, and you are coming through the UCI optical based retimer, and then on this side you are connecting with a pool of pooled memory, shared memory. You have a set of accelerators, so when you need more memory, you can go to that pool and get that memory. And it will be very high bandwidth, because we are going to see the bandwidth density in UCI is fairly high. Optics has the promise of delivering very high bandwidth. So this makes the vision possible that you have composable systems, not just at the package level, not just at a node level with CXL PCIe, but also at the rack level and beyond with co-packaged optics combined with UCIe. So this is what I call is the money slide. If we look into UCIe, what are the characteristics and what are the key metrics, right? We talked about most of these characteristics here. Data rates are 4, 8, 12, 16, 24, 32. The width of the cluster is 16 and 64 for standard and advanced. Bump pitch is 100 to 130 micron for standard and 25 all the way to 55 micron for advanced package, and the channel reach is 25 millimeter or less for standard and 2 millimeters for advanced package. So with that, let's look into the bandwidth density here. We give that bandwidth density as both linear and aerial. So when it is linear, it is gigabytes, not gigabits, gigabytes per second per millimeter. A lot of people, they're used to gigabits. We always give things in gigabytes. gigabytes per second per millimeter, and the bandwidth density aerial is gigabytes per second per square millimeter. And what you see here is a set of numbers. So for example, this goes 28 to 224, 165 to 137, so on and so forth. You can read the number, but fundamentally, let's take this column here, right? What it says is that at 4 giga transfers per second, a single module of UCIe in the advanced package, which is 64 lanes, gives you 188 gigabytes per second per square millimeter. And these are, by the way, conservatively estimated at 45 micron bump pitch. If you run at 8 gig, you're going to get 376 gigabytes per second per square millimeter. So it keeps multiplying, right? And if you run at 32 gig, you're going to get 1350 gigabytes per second per square millimeter. So that's more than a terabyte per second per square millimeter of bandwidth. By the way, we are still, and this includes, when I give the numbers, this includes the die-to-die adapter, everything, right? Your clock distribution, everything is included. And we are still bump limited. We expect these technology to be bump limited because the circuits are so simple. So if you go to 25 micron, this bandwidth density, for example, the aerial density from 45 to 25 will go up by about 3.25x. In reality, what will happen is people are just going to reduce the frequency and do much better in terms of power, because what are we going to do with so much of bandwidth, right? It's a good problem to have. So we might as well just get even lower power. Picojoule per bit. This is the peak power, 0.5, 0.25 picojoule per bit. Okay, let me give a comparison point here. PCI Express, again, the technology have been involved in from the beginning, right? And CXL. Comparable numbers here, you'll be lucky to get 10 gigabytes per second per square millimeter. Why is that? Because once you are escaping the package, once you are going through a channel, external channel, you are going through connectors, it's fairly tough, right? I mean, tough to design. So you are basically trying to drive the thing as fast as you can. You are no longer bump limited, you are circuit area limited. So you're fundamentally expecting 2 to 3 orders of magnitude, 2 to 3 orders of magnitude better bandwidth density, and I would expect nothing less, because this is a much better channel. If we did our jobs right with engineering this, we would be getting all this benefit, which we are getting. Power efficiency wise, we are 0.25 and 0.5. External interconnects like PCI Express, CXL, all of those, they get 5 to 10 picojoule per bit. And again, these are much more, complicated circuitry, which you need to do because, you're going through all those channel losses there. Low power entry and exit, another key criteria, right, for that linear, the scalable power consumption that I mentioned. 0.5 nanosecond for less than 16 gig and 1 nanosecond for 24 and 32 gig. So if your internal clock is running at 2 gigahertz, that's literally in one clock, you are able to turn your circuits on or off and saving 85% of power. I would like to save 100%, but we all know there is leakage, all of those things, right? But that's 85% is really good in terms of power savings. So it doesn't quite get me to that, power line which starts from 0, but at least it comes very close. Comparable number on PCI Express or CXL, to wake up those circuits takes multiple microseconds, not nanoseconds, microseconds, multiple microseconds. And again, those are complicated circuitry, they need to retrain all of those things, right? So it takes a while to turn those on or off here, because these are very simple things. We can just literally turn them on and off. When there is no demand, we can turn them off. 2 cycles later, we can turn them on, right? And get to the power savings we want. Latency, transmitter plus receiver, about 2 nanoseconds. Again, from the FDI interface, die-to-die adapter pin and back, right? Comparable numbers in the CXL, for example, link layer to physical layer pin and back, 20 nanoseconds. So again, this is what I would expect because it's a much more simpler thing. Reliability, we measure reliability in FIT, which is failure in time. How many failures do you get in a billion hours? And when we measure our reliability, we do the calculation, we get 10 to the power minus 10. Anything less than 1 is good. In general, I try to shoot for 10 to the power minus 3. Beyond that, it's whatever. Doesn't matter, right? At that point, it's 10 to the power minus 10, 10 to the power minus 20, it's close to 0. In reality, right, if you look into silicon fit tends to be in 3 digits or 4 digits. So what you really want is your interconnect, and whether it is external or internal on package, doesn't matter, right? If you look into PCI Express, the same story, CXL, right? We want it to be less than 10 to the power minus 3 for the maximum width possible, and we are happy with where we are. So in general, best KPIs, and we believe this is going to meet the needs of the market for the different areas of compute till the end of the decade. But we are not sitting quietly, right? We have other aspirations. We are working on those things. All right. So what are the ingredients that make a broad interoperable ecosystem? Again, comes from us as a collective industry having done very successful standards at the board level, right? It's at the intersection of these 4 concentric circles. I don't know how to draw circles, so it's oval. So of course, you need to have a broad market. You need to make sure that manufacturing, packaging, test, those capabilities exist. And as I said, they already exist because people are constructing chiplet-based packages today, and it's in volume market. So those capabilities do exist. Chiplets and chiplet-based product attach points, those are important. And as you can see, we have a lot of members companies here. So other aspect is very well-defined standards with KPIs. So die-to-die specs well-defined across the entire board, not just one aspect, but look at the picture in a holistic manner. And most importantly, compliance and interoperability. So that will result in test tools, procedures, all of that, and basically want people to have a predictable path. And of course, availability of die-to-die IPs, verification IPs, tools, methodologies, and you can look into the numerous announcements that a lot of the IP and VIP companies have made since last year, right? So UCIe we announced in March of last year, little over a year old, and a lot of companies have announced the IPs in various process nodes. You can go and look into those. So that was my part. If there are any questions, Nathan should take them.
Yeah, let's go to questions. If folks have questions, please use the microphone. State your name and affiliation. That would be wonderful. And then we also have some questions on the Slack. Deepak, you want to go with that first?
Yeah, this question is from Michael Mortensen from Skyworks. Will the UCI consortium provide a patent shield for the current and future packaging technology similar to PCI SIG?
Sorry, what was the question?
So can you repeat the question?
Yeah. So will the UCI consortium provide a patent shield for current and future packaging technology similar to PCI SIG?
Yeah, do we get the IP protection for the packaging technologies?
IP protection for the packaging.
Yeah. Similar to PCI SIG.
Yeah. So the UCI has the same, similar, I should say, IP as PCI SIG. CXL has its FRAND-based technology, fair, reasonable, and non-discriminatory. I'm not a lawyer, so you should look into all of those things. But IP model is expected to be very similar to those.
Yeah. Let's take a question.
Let's take questions from the room.
Yeah.
Hi, Charlie DeMergent from Semi-Accurate. You showed the old way, which was PCIe, and the new way, which is UCIe, more or less. PCIe had systems composable by the end user or maybe OEM level. UCIe is basically composable at the foundry level. Is there any work being done by anyone to kind of split the difference where you can have a composable system on advanced packaging that's not necessarily done and baked at the foundry, that's somewhat modifiable? I understand the trade-offs, but just maybe like a large OEM like a Dell could do the composition or some of the composition at their level and gain some of the benefits.
Yeah. So if I were to, so a company like, let's say, cloud service provider, they can go and get different chiplets from different places and assemble them anywhere. So from that point of view, you're not bound by a given foundry, right? You can get your chiplets from different foundries and you can do the mix and match. You can come up with whatever is the requirement that you have as a end user in that case, right? Of course, this will be for example, a Dell or a cloud service provider or whoever, right? And then they can assemble the package themselves. Yeah.
I understand that, but I'm talking something more like halfway through the life they want to upgrade the NIC.
Yeah. Okay. So you're talking about, can I do a hot plug at a package level? Yeah.
A socket, for lack of a better term, gains much of the benefits.
Yes. So because these are all already assembled on the package, you can't really remove a chiplet, but you can go through halfway through and then decide that, hey, I need to upgrade my accelerators and on this set of accelerator, but keep the rest of the infrastructure the same. So you can go ahead with a new packaging and upgrade your accelerator, because even if there is no way for you to really pull something out.
That's what I'm talking about.
Yeah, you really cannot pull out anything out of a package. At least not yet, right? If, hopefully that will happen one day, right? But it's a reflection of the existing capabilities of the technology. But you should be able to, the ultimate goal here is that you didn't have to redo all the other work, right? You only replace the component that you really need.
Okay, thanks.
Yeah.
Go ahead.
All right, Nathan Brookwood from Insight 64.
Yeah.
You've gone to great lengths in UCIe to sort of preserve the semantics of the PCIe interfaces in UCIe. Can you give us one or two real-world examples of where that compatibility between the chiplet stuff and the system stuff really has proved to be beneficial to some designers or customers?
Sure. So let me give you some examples. For example, if I want to take a NIC, it has got very high need for bandwidth. I can take advantage of the system memory that is attached on the other side. I can connect it on the package and get that benefit. Or if I want to, let's say, do some video processing, for instance, right? I need a lot more bandwidth. I can, of course, do it on PCI Express, but then I'm taking up from my precious slots there, right? I can put that on the package. Its power consumption is, let's say, 20 watts, which is fine, which is a reasonable number. I can put that. It consumes a lot of bandwidth, but that power consumption is a lot less. And I can go ahead and do those kind of things, right? So effectively, today, if you look into what we do, right, or on-package memory, for instance, right? There are several examples that we can have, right? So all of these are good examples of things that we want to do on package. And of course, you want to do, like we talked about co-packaged optics, talked about, some kind of, for example, a modem that you want to do if you're in the client segment, right? I mean, those are all great things for UCIe to be used for.
And do you think that the compatibility in terms of the interfaces facilitates that? Couldn't you do it if they weren't compatible?
Compatibility with those interfaces helps you, because those are you have your software infrastructure in place already, so you don't have to go through any of those. You don't have to redo new software, right? You can even test it out as a discrete part and then integrate it on the package. So that's where these things are going to be really helpful in terms of carrying it forward, right, or a lower barrier to entry. If you look into, what we have really leveraged is just the protocol. We have not taken into, we basically have done our own effectively link layer and physical layer completely differently, because that's where really we get the best KPIs.
Okay, thank you.
Yeah.
Go to Mark.
Yeah.
Mark Hill, Wisconsin, and Microsoft.
Hey, Mark.
Great work. So, from your decades of experience with protocols, what do you think is going to gate when UCIe is successful?
So, success means different things, as you very well know, right? With CXL, right, we have been on that journey together. Success means different things at different points of time. So this CXL we introduced the consortium in March of last year. When I look back at the journey with CXL, we are, significantly probably, if not significantly ahead, we are definitely not behind. I think we are trending ahead of that, which is always a good thing, right? Anytime you do something in that quick of a success and you want to do better than the last time, right? So that's there. I think if you're asking about, when will products show up, of course, we are not at the liberty of talking about people's product plans and all of that. But here is what I'm going to say. If you look into CXL, started in 2019. By 2022, you had products out there in the market, right? So that kind of gives you like the time horizon that people take. And then, the IPs and VIPs and everything else in CXL were defined within a year. They were publicly available. They are already available here. So I think we are on a very good path here to.
But don't you think Foundry plug and play is easier said than done?
Foundry plug and play is going to be, it has got more challenges than clearly at a board level. But again, this is a bigger challenge than probably at a board level kind of thing. So you're right in terms of that. But I think we will make this one happen based on where I see all the trends are. Yeah, thank you.
We'll take one question from Slack and then we'll come back to you.
Yeah.
Deepak.
Yeah, Shomit Das from Samsung asks, how does on-die integration work? Will it support a split foundry manufacturing model?
So, yes, it supports on package is what I'm assuming they meant, right? So yes, if you can get dies from different foundries and package them together, it works. And that's, by the way, nothing novel, right? If you look into a lot of, including my own company's products, we have assembled up to 47 chiplets on the same package from, I believe, 5 or so different process nodes. So not just from Intel, but from other TSMC also, right? So that's possible. And I think, Mark, going back to your question, right? I mean, we have proven that that model can work. So the question is that, do you have a well-defined spec? Have you defined the proper bump map and all of those to make those things happen? Do you have a compliance program for people to generally test out things, right? Yeah. Beyond that, it's going to be, of course, you're going to have to debug all of those things. Those are given. Those happen in PCIe, CXL, everywhere, right? It's not, Yes.
So, Maulik Dada from Microsoft. My question is, say, PCI and CXL, those are packetized interfaces, basically, right? So interoperability will be easier in this case, right? How would you say for streaming mode where all these EXL, AXI, CHI, AXI stuff, they are not packetized? How do we make sure the interoperability still works?
Yeah. So I'll let, without going through specific protocols, those are also, there are two options available. One option is that they can be packetized. By the way, I'll let Marvin talk to it whenever his time comes, okay? But those are packetized. And that's the reason why in the UCI 1.1, we made them be packetized. Even if it is not packetized, even if you go through in the raw mode, we have made it work, even in our own companies. So yeah, that's, you make something, you define it reasonably well.
In the same company, that makes sense. But if you are taking a third-party chiplet or somebody else,
no, it is
right,
packetized. By the way, you can make it packetized. The packaging is not rocket science either.
Totally, but everybody has to be in the same way, right?
Yeah. Of course, they have to be. You just need to make sure that when you packetize it, the bit definitions are clear and all of those things. Absolutely, yeah.
Okay.
Yeah.
Okay. One last question, Debendra.
Jeff Smith, Citadel Securities. So thank you very much for the talk, and I think you've done a good job making the case for the incremental benefit of the UCIe approach over discrete card interfaces as far as bandwidth density, power, and so forth. But as far as trajectory and kind of drawing the border at the other end of the spectrum, are you planning to someday have even more direct physical integration? Is there going to be a die-to-die copper hybrid bonding spec in the future,
Sure.
or are you drawing a line because like the 30 gigabit SerDes is not probably what you want to do in that end, or? what's the future kind of look like?
Yeah, we stated this actually very publicly when we went public with UCI 1.0 back in March. So I'll just state it again. We see the future going forward as 3D also. So we're going to work on 3D. Hybrid bonding is what you mentioned, right? Lower bump pitches, which means even more stringent KPI needs. And what I can say is we'll make it happen. We have done our preliminary analysis. It looks really good.
Do you think it would be
that
a
has
breaking
to
change?
conclude it.
Sorry.
Sorry, Jeff, you can have a discussion later on.
Yeah.
Out of time now.
All right. Hey, thank you very much.
Thank you, Debendra. All right, our next session is on UCIe Protocol, and we have two speakers. Marvin Denman. Marvin has been an architect and designer for NVLink and other high-speed interconnects at NVIDIA for more than a decade. Prior to NVIDIA, he worked on x86 processors at both Intel and AMD, PowerPC processors at Freescale, Motorola, and the Somerset Alliance. He currently co-chairs two UCIe working groups, protocol and automotive working groups. Marvin has an MSEE degree from University of Texas and a BS in computer science from Texas A&M University. Swadesh Choudhary is an I/O architect and technical lead in the I/O technology and standards group at Intel. Over the last 10 years, his contributions span across many interconnect technologies, including PCIe, CXL, chiplet interconnects, coherency, and fabric architecture. Swadesh has been actively participating in the industry standard development of CXL, PCIe, and UCIe. He was a key participant in the development of CXL specification from its inception and continues to author sections of the specification. He is an active contributor in training events for both CXL and UCIe consortiums. Along with Marvin, he co-chairs the UCIe Protocol Working Group. Swadesh has a Bachelor and Master of Technology degrees from IIT Bombay and a MSEE degree from Stanford University. Come on in, Marvin.
Is the microphone working well? Okay. So now that we've had the detailed overview of the UCIe, we'll now start diving into some of the sections and giving you a little bit more detail on how the different sections of the design work. For the protocol section, we want to talk about the protocol layer, which is basically what protocol is connecting into UCIe. The die-to-die adapter, which is actually taking care of the data link layer and those type of activities, and then the physical layer, logical physical layer of UCIe that communicates with the PHY and helps connect them together. The protocol layer, basically the protocols that are currently supported are PCIe and CXL. Streaming is currently defined as a vendor-defined option. In UCIe 1.1, we have added the capability to actually go through the die-to-die adapter with streaming protocols. Before that, for 1.0, streaming bypassed the die-to-die adapter and went directly to the physical layer. And so it was up to the protocol layer to take care of a lot of the work that can be done in the die-to-die adapter. Now, in 1.1, we're standardizing that to where it can go through the same die-to-die adapter that we're using for PCIe and CXL. So it's a much more efficient way of doing things. With the protocols, we have multiple Flit formats. So let's see. Multiple Flit formats are permitted to be in the transport mechanism. A number of those are defined by PCIe and CXL, but basically it's 68-byte formats and 256-byte format of a variety of flavors that we'll get into the details of the variety of flavors for 256-byte formats. Then the raw formats are supported if you want to bypass the die-to-die adapter and go directly to the physical layer. So it would still do all the functions that are in the physical layer on the data so that it can take advantage of everything that's UCIe, but it would be up to the protocol layer to be responsible for correcting data errors and detecting data errors if it is using raw mode. At the physical layer, we have a number of functions. So we have link training functions, lane repair functions, lane reversal, scrambling and descrambling, sideband training and transfers, analog front end and clock forwarding. So there's a number of things that are done at the physical layer that no matter what you're doing, what you're communicating, you're going to need to do at a physical layer to get the communication going at the high speeds that we have for UCIe. While at the die-to-die adapter level, for CXL, we have the ARP-MUX integrated into the die-to-die adapter. So there are two FLIT-aware data interfaces for CXL. We'll get into that in another slide, but basically we can split it up into the CXL-IO and the CXL-MEM interfaces. The CRC is taken care of by the die-to-die adapter. That is inserted as part of UCIe. There's a retry mechanism that is part of UCIe that, based on CRC error detection, that we will retie flits and be able to guarantee correct data across the UCIe link. It also includes, at the die-to-die adapter level, the link state management. So this is similar to what we have for PCIe and CXL. It's walking through the different link states as we initialize the link, as we do things like retrain the links, change speeds on the links. So it has all of that integrated in, and the protocol layer doesn't have to know what's going on there. And then it also, for initialization purposes, has parameter negotiation. There's a lot of different parameters that you can exchange based on either the protocol or UCIe capabilities that you want both sides to be able to communicate during initialization time so that they can successfully communicate when they get to the active state. Oops, wrong slide. Okay. So we have PCIe non-FLIT mode and CXL 68-byte FLIT mode. Those are basically the 68-byte transfer modes of UCIe. In that, we support formats raw, which is basically just send the bytes as is. Retry CRC is applicable. Well, if applicable, the CRC and retry have to be done by the protocol layer. So if you want to send PCIe over the link as raw data, you can do that, and you will be using the PCIe CRCs and the PCIe retry mechanisms. If you want to send it as FLIT data, you can use the 68-byte FLIT format, where retry and CRC is the responsibility of the die-to-die adapter. So UCIe would insert the CRC, and it would check it at the other side, and it would take care of the retry mechanisms that are necessary to guarantee correct data. The framing for this FLIT format follows CXL-IO, the 68-byte format, and it uses packing and unpacking rules for CXL-IO. When we're doing PCIe CXL, the ACK-NAC and PM DLLPs are not used. They're not necessary for this kind of link, but there are some of the other DLLPs are used and are still transmitted along with the data. So what we do is, if those DLLPs are coming in, the CRC is driven to 0 by the transmitter and ignored by the receiver when they're not being used. Okay, sequence numbers are in the message. Frame CRCs, frame parity. So a lot of the information is carried along just like it would be for PCIe. Now, to do this format, the protocol layer is going to drive 64 bytes per FLIT of protocol information on the FLIT data interface. The interface from the protocol layer is just giving us 64 bytes per FLIT, and then UCIe is inserting the CRC and header information that it needs to make it a 68-byte FLIT. This is the same as the FLIT format in the native PCIe or CXL. So the CRC for that size flit is 2 bytes of CRC to cover the 64 bytes of data, and then 2 bytes of header. And then, as we said before, for CXL, the ARB-MUX is integrated into die-to-die adapter. One key point is that 8-bit, 10-bit, 128, 130 encodings, those are not needed for UCIe transport, so you can save all of that overhead and strip that out. PCI flit mode, on the other hand, is a supported format, and it uses a standard 256-byte flit. So you can use the raw format for PCI flit mode, or you can use the standard 256-byte flit. Most commonly, it's going to be the 256-byte flit. In that case, retry and CRC are put in by the die-to-die adapter. Framing follows the same rules that we have for PCIe 256-byte flit packing and unpacking. So this is PCIe 6 Gen 6. Again, the PM and link management DLPs are not necessary, so those are not used, but flow control DLLPs are sent separately over the FDI. So that's another thing. On the FDI interface, we have separated out the DLLPs to a separate interface from the data path, so that the DLLPs can get merged in with data path flits that they need to be merged in with, but they don't have to be replayed. So they're not part of the flits, they're merged in dynamically when we're ready to send them. Okay, then the next mode we have is CXL 256-byte flit mode. So this is using 256-byte flits. We have two different flavors of that. So we have the standard 256-byte flit, which will have the CRC either at the beginning of the packet or at the end of the packet, because there's two flavors of that. And then latency optimized will actually have each half having its own CRC, to make it more efficient to check the CRC on the 128 bytes of data, and then check it again for the second 128 bytes. We're using the 256-byte flit packing rules. Again, PM and link management DLLPs are not necessary. And then for CXL.io, the flow control DLLPs are sent over a separate FDI interface. The die-to-die adapter will insert them into the stream, and they don't have to go through the retry buffer. So the same sort of things that we were talking about on the other format. Now, for streaming protocol, for UCIe 1.0, the streaming protocol is supported in raw format only. So if you wanted to send a streaming protocol, your only option was to bypass the die-to-die adapter and have it go directly to the PHY, to the physical layer. But for UCIe 1.1, we've added the support that can run it through basically in flit modes, just like any other UCIe packets. UCIe will take care of CRCs and reliability and handle it just like any other packets by packing it into flits. So that is an enhancement that was just announced a couple weeks ago in 1.1. The die-to-die adapter. Let's get a little bit into what's going on in the die-to-die adapter. So going through that, we can talk about the functionality partitioning of the die-to-die adapter. We'll give a few example configurations. We can start going into some flit format details. I mean, we've described what flit formats there are earlier, but now we can kind of show some of the details of how the flits are designed. Then there's a protocol and flit format matrix. That's basically saying which protocols support which flit formats, and which are mandatory, which are optional, which are strongly recommended, that kind of thing. There's a state machine hierarchy. These are for things like link states and training states, and we'll talk about that. We'll talk about how parameter exchange is done, and an example of the PM flow. So for functionality partitioning, Debendra had a similar slide to this already, but basically we're split up into the protocol layer. There's a FDI interface, which is a standard interface that's defined for UCIe. It tells you exactly what signals and how you communicate to the die-to-die adapter. Any protocol layer you put on top of this would need to meet this Flit-aware data interface, FDI. Inside the die-to-die adapter, we talked about the responsibilities there, parameter negotiation, link state, CRCs, and an RMUX if applicable. And then the other standardized thing with UCIe is the raw data interface. So basically this is a standard that specifies exactly how the die-to-die adapter is communicating to a physical layer so that you can design it independently to meet the standard on communicating between the two. In the physical layer, we talked about the functions that we're taking care of in the physical layer. I think we did not mention before sideband training and transfers. I don't remember mentioning that on the last time through, but there is a sideband to be able to communicate certain things that the protocol needs to communicate in a reliable way, where the sideband is always running even if the main band is powered down. So CXL, RMUX is absorbed into the die-to-die adapter. The CRC computation is a lightweight CRC. So basically, because of the reliability of the wires, the error rates are low enough that the CRC doesn't have to be an incredibly robust CRC. It's a 2 bytes for every 128 bytes, basically, is sufficient to meet the goals. So it's a lightweight CRC. Flit retry mechanism, we leverage that from PCIe Flit mode. So it's basically similar to what PCIe Flit mode would do. And then link state management flow is used for the reset active PM error flows. And die-to-die specific parameters and protocol specific parameters can be negotiated with the remote link partner. So when we're talking later on, I think we're going to get into more depth on the exact handshakes of how that is done, so that you can see for CXL, for instance, here's how the handshake and how the information exchange. For PCIe, here's the information exchange. So a couple of example configurations. You can do, back up. So you can do a protocol layer communicating directly to die-to-die adapter and directly to a single RDI. So it's like one protocol straight through. For CXL, it would be done like this. So you have CXL.io as a protocol layer, CXL.cachemem as a protocol layer. They have two separate FDI ports, and the RMUX picks between them so that the die-to-die adapter again is a single stack going to the RDI. But then another option that we've added or had on Rev 1.0 of UCIe was to allow two different protocols to be muxed onto the same stack. So in this case, the example is CXL. So we could have CXL for the left side and CXL for the right side, and then there's a stack mux inside the UCIe protocol that can pick between them. So on demand, for Rev 1.0, it would basically alternate between the two and have a bit included in the header that told you which one it was, so that when you got to the other side, you could demultiplex it. So you would have two different protocols going over the same physical connection. Now for UCI 1.1, we've basically made this more flexible to where you can have two different protocols and they can be different protocols. So you could have CXL on one leg, you could have PCIe on the other. You could have CXL or streaming. You could have two different streamings. And you could also dynamically mux between them. Instead of alternating between the two stacks, you can, UCI 1.1, you can on demand. If I have data from this one, I will send it if the other one's not also trying to send. If they're both trying to send, we arbitrate between the two with something that's defined in more detail in UCI 1.1. So we won't really get into that today because that's not really covered in this presentation, but that is a capability that now exists that you should be aware of. So going into the Flit formats, we're going to get into some of the Flit format, or go through the Flit formats. Some of this is a little bit repetitive, but we'll try to pull out anything that's new in each one of these. So in the raw format, we call that format 1. That's the most basic format. In that format, it's 64 bytes of data from the protocol layer, and 64 bytes of data is what you send across the wire. UCIe does not insert CRC, does not insert headers even. You're just sending whatever the protocol tells you over the physical interface. So all bytes are populated by the protocol layer. Everything's up to the protocol layer, but the logical physical layer will take care of what's necessary to communicate it over the link, as far as things like scrambling and all the other things we listed that the physical layer is doing. You can use that for any of the protocols. You can use it for the streaming protocol, but you can also use it for PCIe and CXL. One of the common uses for it for those protocols is for retimers, where you don't want necessarily anything happening. You just want to pass the data straight through in a retimer. And it is mandatory that this particular one be supported for streaming protocol in both UCIe 1.1 and 1.0. So we have to support that at the minimum for streaming. 68-byte Flit format. This is what we call format 2. So in this format, oops, wrong button, go back. So in 68-byte format, we will take 64 bytes from the interface, and for that 64 bytes, we'll insert 2 bytes of Flit header and 2 bytes of CRC. So then the next cycle, we have another 64, and so we'll insert 2 bytes of Flit header and 2 bytes of CRC. And the die-to-die adapter takes care of the alignment necessary to keep shifting this data so that it keeps going. This is used for PCIe non-Flit mode and CXL.io 68-byte Flit mode. So those two formats use it, modes use it. And basically there's 64 bytes on the FDI interface for each Flit. And one thing to point out, I guess, the Flit header itself, it contains a protocol identifier which tells you what protocol it is, a stack identifier, sequence number, so it has sequence number information to help you, and then ACNAC completion and a positive data stream indicator. So the positive data stream indicator is important, particularly for this non-aligned type of format, because if you need to stop the stream, you need to stop it cleanly, but you may be stopping it in the middle of a line or a middle of a 64-bit chunk. So if you have a PDS Flit header here that says, hey, this is the end of the stream, I need to stop this stream, you're required to have 0 fill at the end of this line, and then another 2 64-byte chunks of all zeros, and then you have to get to a 256-byte boundary so that when you end a stream, you'll cleanly get to a 256-byte boundary with that stream, but with zeros so that you can pad at the end when you're stopping the stream and pausing the stream. So that helps the receiver to understand when the transmitter has stopped sending you Flits. PDS Flit header is basically a special Flit header, and it's just followed by all zeros, and there's some rules about how to get to the 256-byte boundary. Now, I think now Swadesh is going to come on.
No? How about now? Yeah. Okay, good. Thank you, Marvin. So I'm going to continue the rest of the
of the talk, and we'll be covering some of the remaining of the Flit formats, and then I'll sort of give some example flows to highlight the die-to-die adapter functionalities, and then we'll end with a very quick summary. We don't have enough time to dive into a lot of the details, but a very quick summary of the logical portion of the physical layer before we switch to the next section. So this format here, people that are familiar with PCIe will look very familiar to them because it is more or less leveraging the 256-byte Flit in the PCIe specification. The main difference being that in PCIe, the last 14 bytes are reserved for an 8-byte CRC and a 6-byte FEC, a forward error correcting code, and that's because the BER of the link requires that. But because the die-to-die link has such a low bit error rate that the probability of failures is so low, we're able to get away with a 16-bit CRC. So we've replaced that with a 10-byte reserved field and 4 bytes of CRC. CRC0 corresponds to the CRC over the first 128 bytes of the Flit, and CRC1 corresponds to CRC over the remainder of the Flit up until the reserved fields, and then the rest of it is shown here. And I'll highlight that we're going through a lot of Flit formats over here, but the primary motivation of supporting these Flit formats is to make it easier for IPs to transition from existing PCI CXL designs over to a die-to-die link. And we're trying to make optimizations and simplifications as applicable for the die-to-die link, but we want to make it easier for people to transition and maintain the IPs for the different cases here. Now, in the case of this 256-byte Flit, the protocol layer will sort of transfer the Flit over FTI in the format shown. It is showing an example of a 64-byte interface. The width of FTI is a parameter. You could design it to be something slightly different, but all the examples shown in this tutorial are covering a 64-byte interface there. But the protocol layer will drive 0 on any of the reserved bits or any of the bits that are filled in by the die-to-die adapter. So that way, when the Flit shows up in the adapter, it knows exactly where to insert the CRC or the DLP bytes. And just like in PCIe, the DLP bytes can carry either Flit marker or the flow control update DLLPs. And that's sort of shown in these bytes over here. So now, similarly, we map the standard 256-byte Flit for CXL onto the die-to-die link as well. And what's shown here is both the formats for CXL.io as well as CXL.cachemem. And again, you will see a lot of similarity with the definition in the CXL specification. The Flit header is in the beginning, and then the last 14 bytes are replaced by a 10-byte reserved field followed by 4 bytes of CRC. And similar to before, CRC0 covers the first 128 bytes, and CRC1 covers the remainder of the Flit. And then, the DLP rules and all of that remains the same as PCIe or CXL.io because those are pretty much the same there. All right. Now, in CXL 3.0, it also introduced certain latency optimized Flits. And we have a couple of flavors of that from the perspective of optimizing things for the die-to-die link. The first flavor, again, to make the transitions easier for designs, is leveraging pretty much everything that CXL specification had defined. The difference between the standard and the latency optimized one is, we had 6 bytes of CRC in CXL. That gets replaced by 4 bytes of reserved fields and a 2 byte of CRC that covers the entire 128 bytes here. And then in the end, we had 12 bytes, 6 bytes of CRC and 6 bytes of FEC that got replaced by 10 bytes of reserved fields and 2 bytes of CRC. So that's the only change, with respect to how the format looks between CXL specification and die-to-die. We made one more enhancement for .io in this format. You'll notice that there's a dedicated spot for DLP and Flit marker that allows you to send a flow control update at the same time as sending a Flit marker when using this format. Because we had a bunch of reserved bytes here, that seemed like a meaningful optimization over here. And again, this is sort of leveraging what was in the CXL specification, but we sort of, because latency is critical for die-to-die links, we gave an enhancement to increase the efficiency of these formats. And so you'll see that in the next format. What you'll notice is that the reserve bits have gotten much smaller, and we're able to increase the link efficiency by giving additional information that can be inserted by the protocol layer. So in the case of CXL cache mem, we had 14 bytes left, and that nicely fits into an H slot definition from CXL, which is a 14-byte slot. So we let the protocol layer insert an additional H slot in these flits. And then in the case of CXL.io, we, because it's usually at a D word granularity, we gave an additional D word for the protocol layer to pad in extra bytes of a TLP. So this lets us get, slightly higher efficiency, but because it's a different format, it's sort of negotiated separately with the remote link partner, and both sides have to support it for it to work and interop. Okay, so that's a lot of Flit formats. This is sort of a summary table trying to sort of give you a flavor of what the matrix looks like. On the rows, we have the different formats. So we have support for 6 formats, including the raw format. And on the columns here are the different protocols. So we go from PCI non-Flit mode, which follows the protocol definitions from PCI 5.0 and before. And then there's PCI Flit mode, which follows the protocol definitions in PCI 6.0, because there's been a lot of enhancements and new fields in the TLPs and things like that. Then we have CXL 68-byte Flit mode, which follows the protocol definitions from CXL 2.0 and earlier. And then we have the CXL 256-byte Flit mode, which follows the protocol definitions in CXL 3.0 for the 256-byte Flits. You will see that the raw mode is optional for PCIe and CXL. The reason it shows up as mandatory in the case of streaming is the column of streaming, the protocol layer interop is obviously going to be vendor defined. As was touched in the Q&A earlier, the specific layout of the bits is up to the protocol layer to define that, and you have to make sure that the person that or the chiplet that you're integrating with supports the exact same definition. But from an adapter perspective, this functionality is mandatory if you want to support streaming, because that's just creating a bypass path for the protocol layer, right? And I should mention, like Marvin said, in UCI 1.1, all of the Flit formats have been opened up for streaming protocol. The slide is still reflecting UCI 1.0, but if you see the UCI 1.1 specification, you will see all of the Flit formats are now accessible for the streaming mode as well. So the protocol layer can leverage any of these formats for reusing the die-to-die CRC and retry flows. And then in case of the other formats, the 68-byte one, that's mandatory for PCI non-Flit mode and CXL 68-byte Flit mode, because it's closest to those Flit formats that are there in those specifications. The standard 256-byte N header one was the one that I was showing that was similar to PCIe. So that's mandatory for PCI Flit mode. The other 256-byte format where the Flit header was moved in the beginning is mandatory for CXL. And then the latency optimized ones, similar to CXL specification, are optional, but we strongly recommended the ones with the enhanced efficiency, with the goal being to encourage the IP vendors to sort of leverage the higher efficiency and improve the latency by using that format for CXL protocols. All right, so now let's talk a little bit about the state machine hierarchy. And the goal in all of these cases, when we are defining like a layered protocol, is to create like a right level of abstraction for the different layers to interact with each other. So below the die-to-die adapter, we have the physical layer. But since this section is focusing on the die-to-die adapter, we're showing state machines inside the adapter. But what happens is that there is a link training state machine inside the physical layer, and it abstracts away the current state of the link. Could be a power management state, could be active, could be retraining, onto the RDI interface. But then the adapter maintains its own state machine that it has to coordinate with the remote link partner in order to create the operational state for the adapter and the protocol layer. And we have a subtle difference between CXL and other protocols in this situation. From a protocol layer perspective, our goal was to make the state transitions look similar to the virtual link state machines that are defined in CXL spec. And because the RMUX functionality was subsumed inside the adapter, the VLSMs is what's exposed on FDI for the protocol layers. Whereas for PCIe and streaming case, the adapter link state machine is directly exposed to the protocol layers. And they have very similar states to deal with, active, retraining, power management, link error handling, link disable, all of those kind of functionalities have been incorporated in these state machines. And then the RMUX handshakes for the virtual link state machines are leveraging the CXL specification and using the RMUX link management packets. But the adapter link state machine handshakes are done over sideband link. I'll talk a little more about this. I have an example of a power management entry flow for the link. All right, so in this slide, I thought it would be interesting to give an idea of showing the different steps and stages of a normal link bring up, right? So you boot the part up, it goes through its reset flows, and then you train up the link and it's ready for protocol transfer. So from the point, you boot things up to the point where the link is trained, sort of a high level abstraction of the different stages and how it goes through the different layers is what's shown here. So once, both the die on either side of the link come up, they have to go through their independent reset flow. Could be things like fuse download, could be, just basic reset bring up until the point where they are ready to train the UCI link itself. So we call that here as stage 0, and notice it could take different amount of time. There's no real coordination until you're ready to begin training the link itself. So that's what's shown in the 2 boxes over here. So once the die are independently up to a point where they're ready to train the link, they start coordinating with each other over the link. And on the link itself, we have 2 sets of signals effectively. There is a sideband dedicated set of pins, and then there is a main band dedicated set of pins. And the reason the sideband is so useful is because it helps us take care of a lot of the auxiliary stuff that we have to do for link management, exchanging training information, coordinating the training bring up itself, and also doing things like register accesses, reads and writes. What that allows us to do is keep the main band data path really optimal for performance and latency, and a lot of the other stuff that we need for link management, we offload it to the sideband link. And because of that, the sideband link becomes very critical. We run it at a lower frequency of about 800 megahertz, and we want that to be like super reliable and always come up, so we're running it at a much lower frequency than main band. And so the first thing that has to happen is just the detection and initialization of the sideband itself, because without that you can't really go ahead and do any of the other steps of the link training. So that's what ends up being the stage 1 of the link bring up. They exchange sideband messages to make sure the sideband link is up. In the case of advanced package, because bump failure probability increases, we have provision for repairing the sideband link as well. But all of that sort of gets detected and done in stage 1 of the link bring up. Once we know that the sideband is functional and reliable, we move on to the main band training. That's what we call stage 2. And this itself, I'll show you sort of a high-level link state machine diagram coming up. But this is where the main band is going to come up and train itself to the highest common supported speed by both sides of the link. And we'll also do things like detect if we need lane reversal, lane repair. We also have provision for doing bit degrade in the case of standard packages. All of that sort of gets done inside stage 2. The link training state machine goes through its entire flow, train the circuits and get them ready for main band operation. We have some parameter exchanges in the beginning of the main band training. These are done over sideband, and that's really required to figure out what is the operational point you're going to settle at. So for example, both sides of the link will tell the other side, this is the highest speed I support. Could be 16, could be 24, could be 12. And then both sides will sort of implicitly assume, okay, I have to train or try to train at the highest common speed that's supported by my link partner and myself. So all of that gets done in stage 2. When the physical layer is good to go at the end of stage 2, it's transitioned to an active state, main band's ready to go. That will be notified to the adapter over the RDI interface. And then the adapter will do another level of negotiation. I have an example of that coming up, where it will try to figure out what is the Flit format that I need to run in, what is the protocol that I need to run in. and other capabilities of the adapter. And that lets us give us that flexibility and isolation. And because these things are being done over sideband, there's not a lot of burden on the main band itself. We can have the functionalities that are sort of isolated to the adapter negotiated independently of the functionalities that are relevant for the physical layer. So the adapter does that exchange over sideband. It figures out the common operating point. And once that is done, it notifies the protocol layer over FDI. It transitions the link state machine to active. And then regular data path flow and transfer can begin. All right, so this is a quick example of a CXL parameter exchange. We have a bunch of sideband messages defined in the specification to cover different aspects of the exchanges. This is just showing one example of a handshake that happens first to negotiate the adapter capabilities. And then once that's established, there's a handshake that happens to negotiate the protocol level capabilities. Things like, are we running all three protocols of CXL.io, CXL.cache, and CXL.mem, or a subset of that. So all of the CXL relevant capabilities are negotiated independently. And similar to PCIe and CXL specifications, we have a notion of a downstream port and an upstream port defined. So the downstream port sends its capabilities to the upstream port first. The upstream port is allowed to change its advertised capabilities based off of that. And it sends it back to the downstream port. And then finally, the downstream port informs the upstream port what the operating point is going to be. And this kind of a handshake between the downstream port and the upstream port is sort of leverage also, with how things happen in CXL. So sort of, again, allowing people to sort of build off of what's there. All right, so real quick, I want to give an example of the power management flow. And I don't want to sort of go into too details in terms of how the handshakes actually happen. But the main point I want to bring up or sort of highlight in this scenario is that there is two aspects of power management. We have a dynamic power management that is done through just clock gating dynamically and not sending flits across. We have a separate valid lane on the main band, and so we can turn off the clock and the valid and get dynamic clock gating. But we do have support for things like L1 and L2, which are defined in PCIe spec, to go into much deeper platform level power states of packet C and packet S and so on and so forth. And so this is sort of showing an example of the deeper power states which require coordination and handshake across the different die. And because it's a layered flow, the way to make that work is to go down the hierarchy as you're getting into the deeper power state. So first the protocol layers, in this case the ARMUX VLSMs, will negotiate between themselves. Once all the VLSMs are in the relevant power management state, then the adapters will enter that. Once all of the adapter LSMs are in the power management state, then the physical layer will enter the power management state. And that's when we consider PM entry complete. And of course, the exit goes in the reverse direction. The physical layer will exit first, then the adapter, and then the protocol layer, so that by the time the protocol layer exits, we are ready to transfer flits again across the link. All right, so real quick in 5 minutes, I want to cover at least a flavor of what's in the logical physical layer. There are a lot of details here that I won't be able to do justice in 5 minutes today, but hopefully that will inspire you to go and check out the specification and dive deeper into this. So like I mentioned, we have a separate valid lane for indicating data transfer, and along with the forwarded clock, that lets us do that dynamic clock gating of turning off the valid and the clock. The transfer is done over an 8 UI granularity, so that translates to about a byte of transfer per valid frame. Then we have interconnect redundancy remapping for advanced package. Like I said, because the bumps are smaller, the failure probability is a little bit higher, and so we give option for lane repair in advanced package for both sideband and main band. And for main band, we have about a couple of repair lanes per 32 lanes of data. And then in standard package, we offer with degradation support. So if you have a by 16 standard package, some of the lanes become faulty, you have the option to degrade to a by 8 link. Scrambling and training pattern generation is obviously a responsibility of the physical layer. We also have support for lane reversal. This becomes important in a standard like this because there'll be different configurations, different bump map, rotations, and things like that. So in order to be able to get the widest interop possibility, lane reversal becomes critical to be able to talk to multiple different configurations. And then, like I've been saying, the link initialization, training, and power management handling functionality is also supported. And then, of course, scheduling sideband messages. So we have a single, strobe and a data lane for sideband. So the physical layer is responsible of accepting sideband packets from different sources. It could be the adapter, it could be the physical layer itself, arbitrating and then serializing and deserializing it over the sideband link. That's part of the physical layer as well. And then real quick before I close, just a couple of minutes on the state machine. We sort of covered a lot of this in the bring up flow that I went through, but this is kind of putting a picture to what's happening inside the physical layer in the different flows. So you can sort of map reset to the state 0. It's waiting for the die to reach the point where it's ready to train the link. SB init is the sideband detection and initialization process. Once that's done, we go into main band init. Main band init is where we will do things like lane reversal, lane repair. Main band init, I'll mention, runs always at 4 gigatransfers per second, since that's the lowest speed and required by all UCI implementations over main band. And then that's where the parameter exchanges happen as well. So that's when you know what the highest supported speed of the remote partner is. And then when you get to MB train, you go through all of the training at the highest speed that you want to train to. And then if you fail at that speed, we have provision to degrade speed and or width, depending on the situation. Link init is just a transitionary state in order to do a sort of very robust sideband handshake to make sure that both sides of the link are ready to receive packets. And at that point, the transfer and notification to the adapter is possible. And then once we're in active state, that's where regular Flit transfer can begin. And that's our operational state, the common state for a lot of the time of the link. We have support for runtime link retraining. And if you notice, that sort of leverages the MB train flow. So we do have support for runtime, link degrade, lane repair, all of those things, because failures can happen in field after the path's been running for several years. And so we do have support for detecting and applying those hooks as part of just runtime link training. And then L1 and L2 map to like the deeper power states that we talked about. Exit from L1 would be quicker because it's just sort of redoing the training, but an exit from L2 requires going back to reset and sort of bring the link back up. So that's it. Yep, that was my last slide. So yeah. So I think the last 4 or 5 minutes for questions. Marvin, if you'd like to come back on stage for questions.
Deepak, do we want to go with the question from the Slack first?
Yeah, sure. So Cliff Young from Google asks this question. What parts of the UCI protocol do I need to use to build an accelerator solution that can work with the high memory bandwidth of HBM stacks, which is in the terabyte per second range? The PCI and CXL modes are not in this in the right bandwidth range. So in this case, do I need to figure out something of the streaming mode, raw transfers, and CRC support myself?
Yeah. Hey, so let me just take that question. So CXL has a brief mention of multi-link support capability. It's not very well defined in the CXL spec, but we can certainly add that. So I'll take an action item to go make that happen. So, but that would be the easiest path. I mean, certainly the proprietary protocol can be used, but that's for interoperability, that'll be much more difficult to do. Go ahead.
So this is Sumit from Google. I had a question about the low power entry and exit latencies of this. So since we are also pitching UCIe as like decomposing already existing SoCs into smaller modular pieces, like does the entry and exit latencies become prohibitive at some point?
Yeah, so if you recall, I talked about sort of three layers of power management that we provision for. The lowest layer is dynamic clock gating. That's what Debendra was referring to in his initial deck, where you still expect 80 to 85% of power savings by just getting off the clock and valid. And that's where having a separate valid helps, where we don't have to continuously send data across the link. So for most cases where you're relying on fast entry and exit, that's the mode you want to be in, and be really aggressive about dynamic clock gating in the design. Then we have the second and third tiers of L1 and L2, which sort of map to overall platform states. And if you're going into a deeper platform state, then obviously the entry and exit is going to be relevant from that perspective. But you can tolerate a little bit of higher entry and exit latencies over there. I will mention that because the link itself is a fairly simple link, the time it takes to retrain and train the link is very low. And so even for an L1 exit, I would expect it to be much, much faster than, say, like a PCIe link that it would take.
And
but again, that's only for like a deeper power state if you want to go get that.
In the L1 exit latency, would that be in nanoseconds or microseconds or any?
So a lot of it depends on the implementation, of course. If I had to speculate, I'd say sort of low microsecond range would be reasonable.
Thanks.
Yeah, go ahead.
Jeff Sitzek, a question about the comparative latencies between the 68-byte Flit mode, the regular, and then the lower latency 256-byte Flit modes. So what are the absolute values or the comparative latency deltas on those?
Yeah, great question. And I'll mention that again, obviously, when you talk about like the 256-byte or the latency optimized 256-byte Flit mode, the latency that we quote in the spec is from the first byte that leaves the FDI to the first byte that's received on FDI. Now, obviously, in the case of a 68-byte Flit mode, you have to wait an additional cycle to get the CRC before you know that the Flit is okay to consume. And then similarly, in the 128-byte Flit cases or the 256-byte Flit cases where the CRCs are towards the last part of it, you're going to have to wait for the CRC to show up, whether you know that half is good or not. But in the latency optimized Flit cases, we have the CRC in the beginning, in the first half itself, so you can consume that faster. And I'll just end with, because we're running out of time, is that on the FDI interface, we've provisioned for certain latency optimizations in terms of sort of canceling the Flit that lets you sort of zip the Flit through the protocol layer and then tell it later that the CRC failed. So you can take advantage of things like that.
Okay, yeah, thank you very much, guys, for your talk.
All right, let's give a hand. Sorry about that. We're going to have more time at the end, so we'll take the questions now. Thank you, Marvin.